Welcome to Science for Sleep. Tonight we are not in a hurry. There is nowhere urgent to be, no countdown clock, no engines firing, no pressure to arrive. Instead, we begin with something much quieter. We begin with a question. How long would it actually take to reach the planets? Not in imagination, not in science fiction, but in reality, measured, carefully, slowly. Before we travel anywhere, though, we need to understand something important. Space is not what it feels like in pictures. It looks close. It looks compact. Planets appear lined up neatly in diagrams. Orbit paths are drawn like tidy circles. But those drawings are not to scale. Not even close. If they were drawn accurately, the page would be almost empty. The planets would be tiny specks, separated by vast, silent distances. And that silence matters, because distance is the true story of space travel. When you look up at the night sky, the moon feels near. Mars feels reachable. Venus glows brightly enough to seem almost approachable. But feelings are not measurements. And in space, measurements are everything. So before we leave Earth, let us slow down. Let us prepare the mind. Let us build a sense of scale. Imagine standing outside on a quiet evening. The air is cool. The world feels still. Above you, the sky stretches endlessly. Now imagine Earth beneath your feet. A sphere nearly 13,000 kilometers wide, spinning gently, turning once every 24 hours. At the equator, you are moving through space at over 1,600 kilometers per hour. And you do not even feel it. Already you are traveling. Already you are in motion. Earth itself is orbiting the Sun at nearly 30 kilometers per second. That is more than 100,000 kilometers per hour. And still you feel calm. Still you feel still. Motion in space is strange like that. It can be immense and invisible. Now imagine lifting slowly away from Earth. Not fast, not violently. Just rising higher and higher. Cities grow smaller. Clouds become thin white streaks. The blue of the atmosphere fades into black. At about 100 kilometers above Earth, you cross what is often called the edge of space. It is not a wall, it is not a gate, just a gradual thinning. Air becoming less and less, until there is almost none at all. This is where orbit begins. An orbit is a kind of falling, a sideways fall that never lands. The International Space Station circles here, about 400 kilometers above the surface, traveling at roughly 28,000 kilometers per hour. At that speed, it goes around Earth once every 90 minutes. Think about that. 90 minutes. A sunrise, a sunset, 16 times a day. And yet, this is only low Earth orbit. We have not even begun to approach another planet. To reach orbit, rockets burn enormous amounts of fuel. Most of the energy is not spent moving forward. It is spent escaping gravity. Gravity is patient. Gravity holds tightly. To leave Earth entirely, a spacecraft must reach escape velocity, about 11.2 kilometers per second. That is 40,000 kilometers per hour. Even then, you are only free of Earth. Not close to Mars, not close to Venus, not close to anywhere else. You are simply no longer falling back. Now imagine traveling at the speed of a commercial airplane, around 900 kilometers per hour. If you could somehow drive straight upward into space at that speed, It would take you nearly 18 years just to reach the moon. 18 years at airplane speed. And the moon is our nearest neighbor, about 384,000 kilometers away. The Apollo missions reached it in about 3 days. 3 days feels quick. But that required a Saturn V rocket, one of the most powerful machines ever built. And even that journey covered only a tiny cosmic distance. Now, let us imagine something faster. The fastest spacecraft humanity has ever launched. NASA's Parker Solar Probe. At its highest speed, it moves at around 190 kilometers per second. That is nearly 700,000 kilometers per hour. Incredibly fast. At that speed, you could circle Earth in less than 4 minutes. And yet, even that speed is small compared to space itself. Because space does not measure in kilometers alone. It measures in millions, in billions, in units so large that the human brain resists holding them. Before we continue outward, we need to understand one more thing: the illusion of closeness. In textbooks, the planets are drawn side by side. Mercury, Venus, Earth, Mars. Each one separated by a small gap. But if Earth were the size of a marble, about 1 centimeter wide, then the moon would be about 30 centimeters away. Not touching. Not close. And the sun? The sun would be more than 100 meters away, a glowing sphere across a field. And Jupiter? Hundreds of meters farther still. The outer planets would be kilometers away, on a walking scale. And between them, almost nothing. Space is not crowded. It is mostly emptiness. Profound emptiness. This is why reaching another planet takes time. Not because we are slow, but because the distances are immense. Even light, which moves at 300,000 kilometers per second, takes time to cross space. Light from the sun takes about 8 minutes to reach Earth. 8 minutes. When you feel sunlight on your face, you are feeling something that began its journey minutes ago. Light from Jupiter takes over 40 minutes to reach us. Light from Neptune, more than 4 hours. And light is the fastest thing in the universe. Nothing with mass can match it. So when we ask, how long would it take to reach each planet? We are asking a question about distance, about energy, about physics, and about patience. Because space does not reward haste, it rewards precision. To travel from Earth to another planet, we cannot simply aim and fire. Planets move. They orbit the sun at different speeds, in different paths. To reach Mars, for example, we must wait until Mars and Earth are aligned correctly. This alignment happens roughly every 26 months. If you miss the window, you wait. There is no shortcut, only timing. This method of travel is called a Hohmann transfer orbit. It is an elegant curve, an arc that stretches from one orbit to another. Not the fastest possible path, but the most fuel efficient. And in space, fuel is precious. Every kilogram launched from Earth costs energy, and money, and planning. A spacecraft carries only so much. Once it burns its fuel, it must rely on gravity, or coast quietly. This is why some missions take years, not because they are inefficient, but because they are careful. To reach Mercury, for example, you might think it is easy. It is closer to the Sun than Earth, but Mercury orbits very quickly. To reach it, a spacecraft must slow down significantly. It must fall inward toward the Sun, and resisting the Sun's pull requires complex gravity assists. The Messenger spacecraft took over 6 years to enter orbit around Mercury. 6 years for the closest planet to the Sun. Already time stretches. Already patience grows. But we are still near home, still within our solar system, still within what astronomers call our cosmic neighborhood. Beyond Neptune lies the Kuiper Belt, a region of icy bodies, and beyond that, the Oort cloud, a distant spherical shell of comet-like objects, thought to extend perhaps halfway to the nearest star. We have never seen it directly, but we infer its existence. If Voyager 1, traveling at about 17 kilometers per second, continues outward, it may take 300 years to reach the inner edge of the Oort cloud, and perhaps 30,000 years to pass through it completely. 30,000 years, and still not near another star. Let that settle gently. We have not yet left our own gravitational backyard, and already time feels different. Already distance feels vast. But tonight is not about rushing through numbers. It is about understanding them, feeling them, allowing the scale to unfold slowly. Because the story of travel time in space is not a story of speed. It is a story of distance. And the universe specializes in distance. So before we leave Earth entirely, before we point ourselves toward Mercury or Mars, take one more moment here. Picture Earth again. Blue, bright, turning quietly in the dark. Every human who has ever lived has lived on that surface. Every story, every dream, every question. And from that small sphere, we attempt to cross millions of kilometers, sometimes billions. With machines built by fragile hands, it is extraordinary and humbling and deeply patient. Tonight we will move planet by planet, gradually from the inner worlds outward, measuring distance honestly, measuring time realistically, not in fantasy, but in physics. And as we drift farther from Earth, you may begin to feel something subtle, a sense that space is not empty, but expansive, not cold, but quiet, and that travel there is not fast, but deliberate. We have not even reached Mercury yet, and already the journey feels long. Let us pause here. Let the scale settle. In the next part, we will begin measuring distance properly. We will define the units astronomers use. We will slow down even further and prepare to step carefully into the true architecture of space. For now, rest in orbit above the turning Earth, where time moves gently and the universe waits. Before we travel to Mercury, before we measure Mars, before we calculate the long drift to Jupiter, we need better tools, not rockets, not engines, but units. Because in space, distance is so vast that ordinary numbers lose their meaning. A kilometer is useful on Earth. It measures the road between cities, the width of rivers, the height of mountains. But in space, a kilometer becomes small, almost delicate. The moon is about 384,000 kilometers away. That sounds large, until you compare it to the distance to the Sun. The Sun is about 150 million kilometers from Earth. Now, the moon feels close. Mercury's orbit ranges roughly between 77 million and 222 million kilometers from Earth, depending on where both planets are in their orbits. Those numbers are difficult to hold in the mind. Millions, hundreds of millions. The brain prefers smaller shapes, smaller distances, so astronomers created a new unit, the astronomical unit. 1 astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. It becomes a kind of cosmic yardstick. Mercury orbits at about 0.39 astronomical units. Venus at about 0.72 astronomical units. Mars at about 1.52 astronomical units. Jupiter at 5.2 astronomical units. Saturn at about 9.5 astronomical units. Uranus at 19 astronomical units. Neptune at 30 astronomical units. Pluto averages about 39 astronomical units from the Sun. Even these numbers begin to stretch. 39 times farther than Earth is from the Sun. And still within our solar system. Still within the Sun's gravity. The Kuiper belt extends beyond that, perhaps to 50 astronomical units, and the Oort cloud may stretch thousands of astronomical units outward, possibly up to 100,000 astronomical units. If that sounds enormous, it is. But even 100,000 astronomical units is not a light year. And that is where scale becomes even more extraordinary. A light year is not a measure of time. It is a measure of distance. It is how far light travels in 1 year. Light moves at approximately 300,000 kilometers per second. In 1 second, it could circle Earth more than 7 times. In 1 minute, it could travel 18 million kilometers. In 1 hour, over 1 billion kilometers. In 1 year, about 9.46 trillion kilometers. That is 1 light year. The nearest star system, Proxima Centauri, is about 4.24 light years away. That means its light takes more than 4 years to reach us. When you look at that star, you see it as it was 4 years ago. Light from Jupiter takes about 40 minutes to reach Earth. Light from Neptune takes more than 4 hours. Light from the edge of our solar system takes days. Light from the center of the Milky Way takes about 26,000 years. Already the numbers begin to feel less like distances and more like eras. But here is the quiet truth. Even at incredible spacecraft speeds, we are nowhere near the speed of light. The fastest human-made object, the Parker Solar Probe, reaches nearly 190 kilometers per second. That is astonishing. But compared to light speed, it is about 0.06% as fast, less than 1/10 of 1%. At that speed, reaching the nearest star would take tens of thousands of years, and that is just the nearest one. So, when we ask how long it would take to reach each planet, we must choose our speed carefully. Let us imagine 3 scenarios. First, car speed, about 100 kilometers per hour. At that speed, reaching the moon would take about 160 days. Non-stop driving, no brakes, no slowing. To reach Mars at its closest approach, about 56 million kilometers away. It would take more than 60 years. To reach Jupiter, over 600 years at car speed. Now imagine airplane speed, around 900 kilometers per hour. Mars would still take nearly 7 years. Jupiter, over 70 years. Neptune, more than 400 years. Even at jet speed, space resists haste. Now, consider real spacecraft speed. Voyager 1 travels at about 17 kilometers per second. That is about 61,000 kilometers per hour. At that speed, it took Voyager about 12 years to reach Neptune. It has now been traveling for more than 45 years, and it is still inside the outer boundaries of the solar system, not near another star, not near another planet beyond our own, just drifting outward, patiently, silently. Space is not a highway. There are no straight roads. To travel between planets, spacecraft follow curved paths, ellipses around the Sun, because everything in the solar system orbits the Sun. The Sun's gravity dominates. If you want to go to Mars, you do not aim at Mars. You aim where Mars will be. You launch into an orbit that intersects its orbit. This takes timing, alignment, patience. The most efficient path is called a Hohmann transfer orbit. It uses 2 engine burns, one to leave Earth's orbit, one to match the destination planet's orbit. The journey then coasts, often for months, sometimes years. You are not accelerating the entire time. You are falling gently around the Sun. Energy is the limiting factor. To go faster requires exponentially more energy. To double speed, you more than double the required fuel. And fuel has mass. Mass requires more fuel to move. This creates a quiet trap. The faster you want to go, the heavier your spacecraft becomes, which requires even more energy, which requires even more fuel. This is why interplanetary travel is careful, measured, conservative. Even the most powerful rockets we build today are designed around efficiency, around balance, around windows of opportunity. When Earth and Mars align correctly, we launch. If we miss that window, we wait, sometimes 2 years, because forcing a different trajectory would require too much energy. Time becomes the cheaper resource. In space, patience often costs less than speed. Now, imagine leaving Earth orbit entirely. Your spacecraft reaches escape velocity. You are free from Earth's pull, but not from the Sun's. To leave the solar system entirely, you must reach solar escape velocity, about 42 kilometers per second relative to the Sun. Voyager achieved this using gravity assists. It borrowed energy from giant planets. Jupiter and Saturn acted like slingshots. Carefully calculated flybys transferred orbital energy to the spacecraft. Gravity itself became fuel, but even that boost carries Voyager at only a tiny fraction of light speed. And so it drifts, year after year, beyond Neptune, beyond Pluto, through a region called the heliosphere. The heliosphere is a bubble formed by the Sun's solar wind. It extends far beyond Pluto. When Voyager crossed the heliopause in 2012, it entered interstellar space, but not interstellar distance. That is something much larger. The nearest star is still thousands of times farther away than Voyager has traveled. Let that sit gently. 45 years of travel, and still not even 1% of the distance to the nearest star. Space is not only big, it is layered. Each layer feels large until you see the next. The Moon feels distant until you measure Mars. Mars feels distant until you measure Jupiter. Jupiter feels far until you measure Neptune. Neptune feels remote until you measure Proxima Centauri. And Proxima feels near until you measure the Milky Way. The Milky Way is about 100,000 light-years across. At light speed, crossing it would take 100,000 years. At Voyager speed, it would take billions of years. Longer than human civilization has existed. longer than mammals have existed, longer than complex life has existed. Distance transforms time, and time transforms perspective. When we speak casually about traveling to the planets, it sounds adventurous, bold, exciting. But in truth, it is a lesson in humility. We are a young species living on a small planet, orbiting a modest star, in one spiral arm of a galaxy among billions. And yet, we measure, we calculate, we send machines outward, we stretch curiosity across millions of kilometers. That, perhaps, is the quiet miracle. Not speed, but intention. Not conquest, but exploration. And so, before we begin measuring the travel time to Mercury, before we calculate the months required to reach Mars, let the scale settle once more. Picture Earth again. Just one astronomical unit from the Sun. A comfortable distance. Close enough for warmth. Far enough for oceans. The planets do not sit still. They move continuously. Mercury orbits the Sun in just 88 days. Earth takes 365 days. Mars takes 687 days. Jupiter takes nearly 12 years. Neptune takes 165 years to complete one orbit. Everything is in motion. Everything is dynamic. So reaching another planet is not like driving to a city. It is like throwing a stone into a moving river and predicting where another moving object will meet it. This requires mathematics, precision, timing, and calm patience. As we prepare to move inward toward Mercury, toward Venus, toward Mars, you may begin to sense something subtle. The distances are enormous, yes, but they are not chaotic. They follow patterns, orbits, rhythms, gravitational harmonies. The universe is vast, but it is not disorderly. And that quiet order makes travel possible. Slow, measured, but possible. In the next part, we will finally begin the journey outward from Earth, planet by planet, measuring honestly, starting with the smallest world nearest the Sun, Mercury, a planet that seems close, but resists easy arrival. For now, remain here in the architecture of distance, where kilometers become astronomical units, and astronomical units become light years, and light years become something almost beyond imagination. Let the scale feel heavy, then light, then calm, because the universe does not rush, and neither will we. Now that we understand distance, now that kilometers have become astronomical units, now that light years sit quietly in the background of our thoughts, we can finally begin the journey, not outward first, but inward, toward the Sun, toward the smallest planet in our solar system, Mercury. It seems close. It appears in textbooks as the first planet from the Sun. Just 0.39 astronomical units away, less than half the distance between Earth and the Sun. On paper, it feels near, but closeness in space can be misleading, because Mercury is not just close to the Sun. It is deep inside the Sun's gravity well, and that changes everything. When we launch from Earth, we are already orbiting the Sun at about 30 kilometers per second. Mercury orbits faster, about 47 kilometers per second. To reach Mercury, we cannot simply speed up. We must slow down. We must drop inward. And falling inward toward the Sun requires removing orbital energy. This is one of the great paradoxes of space travel. Going closer to the Sun is not easier, it is often harder, because you must cancel out some of your sideways motion around the sun. Imagine driving around a circular racetrack. Now imagine trying to move to a smaller track closer to the center. You cannot just accelerate. You must reduce your speed. In space, reducing speed requires fuel. A great deal of it. This is why Mercury is surprisingly difficult to reach. The spacecraft Messenger, launched in 2004, did not fly straight there. It performed 1 flyby of Earth, 2 flybys of Venus, 3 flybys of Mercury itself. Each pass used gravity to carefully reshape its orbit. It took more than 6 years before it finally entered orbit around Mercury in 2011. 6 years to reach the closest planet to the Sun. Distance alone did not determine that time. Energy did. Orbital mechanics did. Gravity did. If we imagine traveling at Voyager speed, about 17 kilometers per second, reaching Mercury at its closest approach might take several months. But Mercury and Earth are rarely aligned at their closest distance. Sometimes Mercury is on the opposite side of the Sun. The distance between Earth and Mercury varies greatly. At their closest, they can be about 77 million kilometers apart. At their farthest, more than 220 million kilometers. That variation changes travel time significantly. Even light takes about 4 to 12 minutes to travel between Earth and Mercury, depending on alignment. So imagine a spacecraft traveling far slower than light. Now imagine doing so while carefully adjusting trajectory, carefully conserving fuel, carefully timing arrival. Mercury teaches us our first lesson in planetary travel. Proximity does not equal simplicity. Now, let us imagine traveling at airplane speed, 900 kilometers per hour. At Mercury's closest distance, 77 million kilometers, it would take nearly 10 years. Non-stop. At car speed, nearly 90 years. Even at the speed of a bullet train, it becomes generational. Now, consider the Parker Solar Probe at nearly 190 kilometers per second. At that extreme speed, you could reach Mercury's closest distance in roughly 5 days. But that probe does not travel directly there. Its orbit swings close to the Sun repeatedly. Its mission is not to visit Mercury, but to study the solar atmosphere. Even so, its speed reminds us of something important. Speed alone does not guarantee destination. Direction matters. Timing matters. Alignment matters. Mercury is a small world, barely larger than Earth's moon. Its surface is heavily cratered, scorched by sunlight, frozen in shadow. Temperatures swing dramatically. From 430 degrees Celsius in sunlight to minus 180 degrees Celsius in darkness. It is a world of extremes, but its true difficulty lies not in temperature, not in terrain, but in physics. To reach Mercury is to fight the Sun's gravity, to slow down enough to stay, to arrive gently instead of slingshotting past. And so, our first planet already stretches time, already demands patience, already reshapes our assumptions. Now, let us drift slightly outward, not far, just to the second planet, Venus, often called Earth's twin. Similar in size, similar in composition, but dramatically different in reality. Venus orbits at about 0.72 astronomical units from the Sun. It comes closer to Earth than any other planet. At its closest approach, Venus can be only about 38 million kilometers away. Closer than Mars ever comes. Closer than Mercury usually is. This makes Venus the nearest planetary neighbor to Earth, on average. So, how long would it take to reach Venus? Historically, his spacecraft have taken about 3 to 5 months. The Soviet Venera missions, NASA's Magellan mission. More recently, missions like ESA's Venus Express. They followed transfer orbits carefully timed. When Earth and Venus align favorably, the journey can be relatively short. At Voyager speed, 17 kilometers per second, you could theoretically reach Venus in under a month at closest approach. But again, alignment determines reality. The transfer window opens only at certain times. If you miss it, the trip becomes longer. Fuel demands increase, and patience becomes necessary once more. At airplane speed, reaching Venus at its closest would take nearly 5 years. At car speed, more than 40 years. Even our closest neighbor demands commitment. Venus is bright in our sky. The morning star, the evening star. It shines so clearly that ancient civilizations tracked its motion carefully. And yet, its surface is hidden beneath thick clouds. Carbon dioxide atmosphere, sulfuric acid clouds. Surface temperatures hot enough to melt lead. Around 465 degrees Celsius. Pressure at the surface more than 90 times Earth's. Standing on Venus would feel like standing 900 meters underwater on Earth. Dense, crushing, hostile. And yet, reaching it is comparatively easier than reaching Mercury, because traveling outward slightly from Earth's orbit requires adding orbital energy, not subtracting it. We accelerate, we widen our orbit, instead of diving inward. In space, outward can be easier than inward. That may seem counterintuitive, but orbital mechanics is often like that. Venus, in many ways, becomes our training ground. It teaches us about greenhouse effects, atmospheric evolution, runaway climate systems, and planetary divergence. Two worlds born similarly. Two very different outcomes. But tonight we are measuring time, and Venus shows us that planetary travel is not linear. It depends on position, velocity, energy, precision. If we imagine a future spacecraft traveling at 1/10 the speed of light, about 30,000 kilometers per second, you could reach Venus in less than half an hour at closest approach. But such speeds remain theoretical, far beyond our current propulsion systems. For now, months remain realistic. Months of coasting through interplanetary space. Months of quiet telemetry signals. Months of adjusting course by fractions of degrees. Interplanetary space between Earth and Venus is not empty. It contains dust, charged particles from the sun, the faint whisper of solar wind. But it is mostly silence, mostly vacuum. A spacecraft traveling to Venus drifts quietly for millions of kilometers. Sunlight grows slightly brighter as it moves inward. Shadows sharpen. The sun appears larger in the sky. But the journey itself is uneventful. No landmarks, no rest stops. Just mathematics unfolding over time. Mercury and Venus together teach us a profound truth. The inner solar system is not compact. It only appears that way in diagrams. Distances of tens of millions of kilometers separate these worlds. Even at extraordinary speeds, travel requires planning and patience. We are still close to home, still within 1 astronomical unit of the Sun, still in the bright inner region of our system. And already months pass between departure and arrival. Already years of planning precede launch. Already gravity shapes every move. We have not yet reached Mars. We have not yet crossed the asteroid belt. We have not yet felt the pull of Jupiter. And yet the scale is expanding slowly, gently, like ripples spreading outward from a stone dropped into still water. In the next part, we will continue outward to Mars, the planet that captures imagination, the planet most often imagined as our future destination, the red world, close enough to tempt, far enough to challenge. For now, let Mercury's heat fade behind us. Let Venus's bright clouds drift softly into the distance and remain suspended between orbits, where time stretches and distance defines everything. Of all the planets in our solar system, Mars feels the most reachable, not the closest, not the easiest, but the most imaginable. It glows red in the night sky, bright enough to notice, dim enough to feel distant. Ancient civilizations named it after gods of war. Modern scientists name rovers after curiosity. It sits just beyond Earth, at an average distance of about 1.52 astronomical units from the Sun. But distance from the Sun is not the same as distance from Earth, because both Earth and Mars are moving, orbiting, turning in quiet ellipses around the Sun. At their closest approach, Earth and Mars can be about 56 million kilometers apart. At their farthest, more than 400 million kilometers. That is a dramatic difference, and it changes everything about travel time. When Mars is closest to Earth, a journey can take about 6 to 9 months using current propulsion methods. That is the typical duration of a Hohmann transfer orbit, a carefully calculated arc, launched during a narrow window, every 26 months, because that is how often Earth and Mars align favorably. If we miss that window, we wait 2 years. The planets will not hurry for us, so imagine the launch moment. A rocket rises from Earth, escapes gravity, burns engines briefly to enter the transfer orbit. And then, silence. The spacecraft coasts, falling gently around the Sun, following a curved path that slowly intersects Mars' orbit. There is no continuous thrust, no constant acceleration. Most of the journey is quiet. Telemetry signals, course corrections measured in tiny bursts. Millions of kilometers pass silently beneath the spacecraft. If you were aboard such a mission, you would not feel motion. There would be no sense of speed. Outside the window, stars would remain fixed. Only slowly, over months, would Mars grow from a reddish dot to a disk. Now let us imagine traveling at Voyager speed, 17 kilometers per second. At Mars' closest distance of 56 million kilometers, it would take roughly 38 days, just over a month. That is much faster than our current Mars missions. But Voyager never traveled directly to Mars. Its mission profile was different. Gravity assists shaped its trajectory outward toward the giant planets. If we imagine traveling at airplane speed, 900 kilometers per hour, reaching Mars at closest approach would take nearly 7 years. 7 years. For a planet that sometimes appears bright enough to see with the naked eye. At car speed, nearly 60 years. The illusion of closeness fades quickly. even light traveling at 300,000 kilometers per second. Takes about 3 to 22 minutes to travel between Earth and Mars, depending on alignment. So when Mission Control sends commands to a rover on Mars, they do not control it in real time. They send instructions. They wait. Minutes pass before confirmation returns. Mars is close in cosmic terms, but far in human terms. That difference matters. Mars orbits the Sun once every 687 Earth days. Almost 2 years. Its seasons are longer. Its days are similar to Earth's, about 24 hours and 37 minutes. But its gravity is weaker, about 38% of Earth's. Its atmosphere is thin, less than 1% the pressure of Earth's atmosphere, mostly carbon dioxide. Its surface is cold. Average temperatures around minus 60 degrees Celsius. At night, much colder. Mars is not a welcoming world, but it is not unreachable. We have sent many missions, orbiters, landers, rovers, each one taking months to arrive, each one relying on precise calculations, each one launched during a specific alignment. The first successful flyby of Mars was NASA's Mariner 4 in 1965. It took about 8 months to arrive. Since then, travel times have remained similar, because the physics has not changed. Energy remains costly. Efficiency remains critical. Even if we built a spacecraft capable of constant acceleration, say powered by advanced nuclear propulsion, we might reduce travel time to 3 or 4 months, perhaps even less. But that would require immense energy and careful shielding from radiation, because between Earth and Mars lies open space, exposed to cosmic rays, solar flares, radiation that Earth's magnetic field normally shields us from. A human mission to Mars must account for this. Months of exposure, months in microgravity, months of isolation. And then, after landing, months of waiting for the return window. Because returning to Earth also requires alignment. If astronauts land on Mars, they may need to remain there for over a year before planetary positions allow a fuel-efficient return. So, the journey is not just 6 to 9 months. It becomes 2 to 3 years total. Time expands, not only in travel, but in planning. Mars feels close because it is our neighbor, because robotic explorers send us images, because we see dust storms and valleys, because we imagine footprints there. But measured honestly, Mars remains tens of millions of kilometers away, and always moving, always shifting in its orbit. There is something poetic about Mars. It sits at the edge of what feels possible, far enough to challenge us, close enough to tempt us. It is the boundary between the inner solar system and the vast outer regions beyond the asteroid belt. When we look at Mars in the sky, we are looking across space that light crosses in minutes. But spacecraft cross in months, and airplanes would cross in years, and cars would cross in decades. Perspective changes everything. If we could travel at 10% of light speed, 30,000 kilometers per second, we could reach Mars in under half an hour at closest approach. But achieving even 1% of light speed remains far beyond our current capabilities. The energy required is enormous. To accelerate a spacecraft to relativistic speeds, you must overcome not only mass, but the increasing resistance described by Einstein's relativity. As speed approaches light speed, energy requirements grow exponentially. For now, our journeys remain measured, careful, patient. Mars also teaches us about delay, because communication delay between Earth and Mars can reach 22 minutes one way. Imagine sending a message, waiting nearly half an hour for confirmation, then responding. Every conversation stretched, every decision slowed. Mars reminds us that even small cosmic distances alter time perception. If you stood on Mars and looked at Earth, you would see it as a bright star, sometimes visible, sometimes hidden behind the sun. Small, fragile, blue. Earth would not feel close from there. It would feel distant, and reaching it would require another 6 to 9 month journey, perhaps longer. Mars sits in a delicate position in our story. It marks the outer edge of what humanity has explored with rovers, but beyond Mars lies the asteroid belt, a region often imagined as crowded, dangerous, filled with tumbling rocks. But in reality, the asteroid belt is vast, objects separated by millions of kilometers, mostly empty. Even crossing that region takes months, but it is not chaotic, it is spacious. Mars is our stepping stone, the last rocky planet before the giants, the last world where sunlight still feels relatively strong. Beyond Mars, distances grow more quickly. Jupiter sits at 5.2 astronomical units, more than 3 times farther from the Sun than Mars. The scale increases dramatically. But tonight, we remain with Mars for a moment longer, because Mars represents something deeply human. Ambition, curiosity, persistence. We have sent robots there for decades, each mission building upon the last, each one taking months to arrive, each one proving that distance can be crossed, but not hurried. Traveling to Mars is not about speed alone. It is about timing, energy, precision, and acceptance of delay. Mars feels close, because in the cosmic sense, it is. But in the human sense, it is a months-long journey across a silent vacuum. And that quiet space between worlds is where time stretches, where perspective shifts, where patience becomes necessary. As we drift now beyond Mars, toward the asteroid belt, toward Jupiter, you may begin to feel the scale widening. The inner planets are behind us, the Sun slightly smaller, Earth now just another dot. Mars, too, shrinking slowly into the dark. Ahead lies a region where travel time stretches from months into years and beyond. The red planet fades gently behind us. Its dust storms settle in memory. Its orbit continues quietly around the Sun, and we move outward, where distance deepens and time begins to lengthen. Beyond Mars, beyond the scattered stones of the asteroid belt, the solar system changes, the light grows softer, the distances widen dramatically, and ahead, dominating everything in its region, is Jupiter, the largest planet in our solar system, a world so massive that it contains more than twice the mass of all the other planets combined. From Earth, Jupiter appears as a bright, steady light in the night sky, sometimes outshining every star. It looks close, almost calm, but in reality, Jupiter orbits the Sun at about 5.2 astronomical units, more than 5 times farther from the Sun than Earth. That alone changes travel time significantly. At its closest approach to Earth, Jupiter can be about 628 million kilometers away. At its farthest, more than 930 million kilometers. Even at its nearest, that is over 10 times farther than Mars at closest approach. Now imagine the journey. A spacecraft leaving Earth must not only escape Earth's gravity, but reshape its orbit to reach a planet much farther from the Sun. Unlike Mercury, where we had to slow down, or Mars, where we widened our orbit modestly. Reaching Jupiter requires climbing outward much more dramatically. The Hohmann transfer to Jupiter typically takes about 2 to 3 years. That is the minimum fuel-efficient time. The spacecraft launches, performs a burn to raise its orbit, and then coasts for years, falling slowly around the Sun along a vast elliptical arc. The Galileo spacecraft, launched in 1989, reached Jupiter in 1995. It took 6 years, but that included gravity assists from Venus and Earth. Gravity assists are quiet miracles of orbital mechanics. Instead of carrying enormous amounts of fuel, a spacecraft can borrow energy from a planet. As it swings behind the planet during a flyby, it steals a tiny bit of that planet's orbital energy. The planet slows by an immeasurably small amount. The spacecraft speeds up. Jupiter itself has acted as a gravity slingshot for many missions. Voyager 1, Voyager 2, New Horizons. Each one used Jupiter's immense gravity to accelerate outward toward the outer solar system. But to arrive at Jupiter and stay there, you must do the opposite. You must slow down. The Juno spacecraft launched in 2011. It arrived at Jupiter in 2016, 5 years later. During those 5 years, it traveled nearly 2.8 billion kilometers. Not in a straight line, but along a carefully shaped trajectory. It even performed an Earth flyby 2 years after launch to gain additional speed. Imagine that, launching away from Earth and then returning close to Earth to steal a little more momentum before heading outward again. Interplanetary travel is rarely direct. It is elegant, curved, patient. Now let us imagine reaching Jupiter at Voyager speed, 17 kilometers per second, at its closest distance of 628 million kilometers. It would take roughly 428 days, more than a year, non-stop. At airplane speed, more than 79 years. At car speed, nearly 700 years. And Jupiter is not the edge of our solar system. It is only the beginning of the giant planets. Jupiter's immense gravity shapes the architecture of the entire solar system. Its mass acts as a kind of gravitational anchor, deflecting comets, capturing asteroids, protecting inner planets from some impacts, but also sending objects inward. It is both shield and sculptor. As you travel toward Jupiter, sunlight weakens. At Earth, sunlight takes 8 minutes to arrive. At Jupiter, it takes about 43 minutes. The Sun appears smaller, less intense, still bright, but diminished. Solar panels must be larger. Energy becomes precious. The spacecraft Juno uses enormous solar arrays, long extended wings, to gather enough sunlight even at that distance. Earlier missions relied on nuclear power sources, radioisotope thermoelectric generators, quietly converting the heat from radioactive decay into electricity. Because solar energy fades quickly as distance increases. By the time you reach Jupiter, The sun's light is only about 4% as strong as it is at Earth. Space becomes darker, colder, more distant from warmth. Now, imagine standing near Jupiter. Of course, there is no solid surface. Jupiter is a gas giant, a vast sphere of hydrogen and helium. Its clouds swirl in bands of cream and rust. Storms rage across its atmosphere. The Great Red Spot, a storm larger than Earth, has persisted for centuries. Jupiter rotates rapidly, once every 10 hours. Its magnetic field is enormous, its radiation belts intense. A spacecraft approaching Jupiter must endure harsh conditions. Radiation can damage electronics, shorten mission life. Juno's orbit is carefully designed to minimize exposure. It passes close to the planet, then swings far away, again and again, like a cautious observer. Because Jupiter does not merely sit in space, it dominates its region. Now let us reflect on the scale. Earth is 1 astronomical unit from the Sun. Jupiter is 5.2. That difference may seem small in number, but in reality it represents hundreds of millions of kilometers, and the travel time increases accordingly. Mars required months. Jupiter requires years. And beyond Jupiter, the scale stretches further still. Saturn sits at 9.5 astronomical units, nearly twice Jupiter's distance from the Sun. The outer solar system is not evenly spaced. Distances expand dramatically. As we drift now beyond Jupiter's orbit, imagine looking back toward Earth. Earth would no longer be visible to the naked eye, just a faint star, perhaps indistinguishable from others. Communication delay becomes significant. Light from Earth takes about 35 to 52 minutes to reach Jupiter, depending on alignment. A message sent from Earth to a spacecraft orbiting Jupiter, and the response returning, could take nearly 2 hours. Every instruction must be carefully planned. Autonomy becomes essential. Spacecraft must think for themselves. In limited ways, Jupiter also hosts many moons, more than 90 known. 4 of them large and remarkable: Io, Europa, Ganymede, Callisto, each one a world of its own. Europa may hide a vast ocean beneath its icy surface. Ganymede is the largest moon in the solar system, even larger than Mercury. Reaching these moons adds complexity, more orbital calculations, more timing, more fuel management. Every additional destination multiplies the challenge. But tonight, we measure time, and Jupiter marks the transition from months to years, from manageable distances to profound ones. It reminds us that our solar system is not compact. It only appears that way in drawings. It reminds us that even traveling at tens of thousands of kilometers per hour, we are slow compared to cosmic scale. And yet, we have done it. We have reached Jupiter multiple times. Each mission a patient arc through space. Each one proof that distance can be crossed, not quickly, but deliberately. As we drift now outward, leaving Jupiter's immense gravity behind, the silence deepens. The sun grows smaller. The cold becomes more pronounced. And ahead lies Saturn, with its rings, its quiet beauty, and travel times that stretch even longer. Jupiter changes everything, because it expands our sense of time, it stretches our expectations. It reminds us that space travel is not about racing, it is about endurance, precision, patience, and quiet persistence. The giant planet fades slowly behind us, its striped clouds dissolving into distance, and we continue outward, into darker space, where years become the measure of arrival, beyond Jupiter, beyond the giant that reshaped our sense of scale, there is another world, softer in color, quieter in appearance, yet just as immense. Saturn, the ringed planet, the one that often feels almost delicate in photographs. Thin golden bands, a pale globe, graceful symmetry. From Earth, Saturn appears as a small, steady point of light. Through a telescope, its rings become visible. Even modest backyard telescopes can reveal them, and for many people, that first sight of Saturn feels personal, intimate, as if it were not so far away. But Saturn orbits the Sun at about 9.5 astronomical units, nearly twice as far from the Sun as Jupiter, and that difference matters. At its closest approach to Earth, Saturn can be about 1.2 billion kilometers away. At its farthest, more than 1.7 billion kilometers. Already, we have crossed into distances measured in billions. The journey to Saturn is not measured in months. It is measured in years. The Cassini spacecraft, one of the most ambitious planetary missions ever launched, began its journey in 1997. It did not arrive at Saturn until 2004. 7 years later. 7 years of coasting through deepening space. 7 years of gravity assists and careful adjustments. Cassini did not travel directly. It flew past Venus twice, then Earth, then Jupiter. Each encounter bending its path, adding speed, saving fuel. This is how outer planet missions survive. Not through brute force, but through choreography. If we imagine a simple Hohmann transfer orbit from Earth to Saturn, the minimum energy path, it would take about 6 years. That is the shortest fuel-efficient route. 6 years to reach a single planet. And Saturn is still within our solar system. Now imagine traveling at Voyager speed, 17 kilometers per second, at Saturn's closest distance of about 1.2 billion kilometers. It would take roughly 820 days, more than 2 years, non-stop, at airplane speed, over 150 years, at car speed, more than 1,400 years. Generations would pass. Civilizations might rise and fall, and still the journey would not be complete. This is the scale Saturn introduces. Beyond Jupiter, sunlight weakens further. At Saturn's distance, sunlight is only about 1% as strong as it is on Earth. The Sun appears smaller, dimmer, still bright in the blackness of space, but distant, cold. Light from the Sun takes about 80 minutes to reach Saturn, an hour and 20 minutes. Light from Earth takes between 67 and 84 minutes to reach Saturn, depending on planetary alignment. So a command sent from Earth to Cassini and a reply returning could take nearly 3 hours round trip. Every maneuver must be planned long in advance, every orbit calculated with patience. Saturn itself is enormous. Its diameter is about 9 times that of Earth, but its density is low. If you could imagine an ocean large enough, Saturn would float. Of course, such an ocean does not exist, but the comparison hints at its composition. Mostly hydrogen and helium, like Jupiter, but with a different character. And then there are the rings, extending hundreds of thousands of kilometers outward, yet astonishingly thin. In many places, only about 10 meters thick. The rings are composed of ice and rock, particles ranging from grains of sand to objects the size of mountains. They orbit Saturn like a vast, shimmering disk. Cassini spent 13 years orbiting Saturn, studying its rings, its storms, its moons. 13 years after a 7-year journey. The mission lasted 20 years in total. 20 years from launch to its final descent into Saturn's atmosphere in 2017. When Cassini ended its mission, it plunged into the planet deliberately, burning up in the atmosphere, to avoid contaminating moons like Enceladus. Enceladus is one of Saturn's most fascinating moons. Small, bright, covered in ice, with geysers spraying water vapor into space. Evidence suggests it hides a subsurface ocean. Reaching Enceladus required reaching Saturn first. 7 years of travel. And yet, Enceladus itself orbits Saturn at about 238,000 kilometers away from the planet, a distance comparable to the Earth-Moon distance. Even within a planetary system, scale repeats itself. Large distances between moons, between ring structures, between orbital layers. As we drift toward Saturn in imagination, picture the Sun shrinking behind us, Earth long invisible, Jupiter a fading memory. Ahead, Saturn grows slowly from a point of light, to a disk, to a sphere, to a world with rings casting shadows upon themselves. The travel to Saturn is quiet. There are no dramatic events during most of the journey, no sudden changes, just steady coasting, occasional course corrections, years of drifting. Time in deep space feels different. For a spacecraft, there is no sunrise or sunset, no wind, no weather, just instruments humming softly, and the faint glow of distant stars. Human missions to Saturn are far beyond our current capability. The radiation environment near Saturn is less intense than Jupiter's. But the distance alone makes crewed missions impractical for now. 6 to 7 years just to arrive, years more to return. Life support systems would need to operate flawlessly for over a decade. Psychological endurance would be tested, resources would be stretched. Saturn marks the boundary where robotic exploration becomes the practical choice. Beyond this distance, time stretches beyond typical human mission planning. Saturn orbits the Sun once every 29.5 Earth years, nearly 3 decades. A child born on Earth would not see Saturn complete one orbit until adulthood. Time behaves differently out here, slower, longer, measured in decades instead of days. And yet, we have reached Saturn multiple times. Pioneer 11, Voyager 1, Voyager 2, Cassini. Each mission proving that even billion-kilometer distances can be crossed, but only with patience, only with planning, only with respect for physics. If we imagine traveling at 10% of light speed, 30,000 kilometers per second, we could reach Saturn in roughly 11 hours at closest approach. But such speeds remain theoretical. Energy requirements are enormous. Shielding against interstellar particles becomes critical. At relativistic speeds, even dust grains become dangerous. For now, we remain within our technological limits. And those limits translate into years. Saturn changes our perception again. Mars was months away. Jupiter was years. Saturn extends into nearly a decade of planning and travel, and yet it is still not the outermost planet. Beyond Saturn lie Uranus and Neptune, ice giants, colder, farther, where travel times extend into a decade or more. As we leave Saturn behind in our slow outward drift, its rings flatten into a thin line, then vanish entirely. The sun dims further, the cold deepens, communication delays lengthen, and the solar system reveals itself as far larger than most people imagine. Saturn teaches patience, endurance, long arcs through silent space. It reminds us that beauty often lies far away, and that reaching it requires commitment measured in years. We continue outward now, beyond the ringed world, toward darker regions, where sunlight becomes faint, and decades of travel become normal. Beyond Saturn, beyond the graceful rings and the golden glow, the solar system grows quieter, colder, more spacious. The sun, once dominant in the sky, begins to shrink noticeably. Its light softens, its warmth fades, and ahead lie two distant worlds, Uranus and Neptune, the ice giants. They are called giants not because they are as massive as Jupiter or Saturn, but because they are large, strange, and remote. Uranus orbits the Sun at about 19 astronomical units, Neptune at about 30 astronomical units. That means Uranus is 19 times farther from the Sun than Earth. Neptune is 30 times farther. These numbers are simple to say, but vast in reality. At its closest approach to Earth, Uranus can be about 2.6 billion kilometers away. Neptune, at its nearest, about 4.3 billion kilometers. Billions of kilometers. This is where travel time stretches dramatically. Voyager 2 is the only spacecraft that has ever visited Uranus and Neptune. It launched in 1977. It reached Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989. 12 years after launch, it finally completed its grand tour of the outer planets. 12 years to reach Neptune. And Voyager did not slow down to enter orbit. It performed flybys, quick passes, gathering data as it sped onward. If we imagine a dedicated mission to Uranus using a Hohmann transfer, it would take roughly 8 to 9 years to arrive. To Neptune, 12 to 15 years. That is with fuel-efficient trajectories. Carefully planned, carefully timed. Now imagine traveling at Voyager speed, 17 kilometers per second, to Uranus at 2.6 billion kilometers. It would take roughly 1,770 days, and nearly 5 years. To Neptune at 4.3 billion kilometers. It would take about 2,930 days, just over 8 years. At airplane speed, reaching Uranus would take over 330 years. Neptune nearly 550 years. At car speed, thousands of years. Generations beyond memory. These are not weekend journeys. They are not decade-long missions for humans. They are multi-decade commitments. The sunlight at Uranus is only about 0.3%, as strong as at Earth. At Neptune, about 0.1%. The sun appears as a bright star, still brilliant against the darkness, but small, remote. Light from the sun takes about 2 hours and 40 minutes to reach Uranus. It takes over 4 hours to reach Neptune. That means when sunlight touches Neptune, it began its journey before many people on Earth had finished their morning routine. Communication delays become profound. A signal from Earth to Neptune can take more than 4 hours one way, 8 hours round trip. Imagine sending a command, waiting nearly half a day for confirmation. Spacecraft must operate independently, with onboard systems managing routine tasks. Uranus is unusual among planets. It rotates on its side, its axis tilted about 98 degrees. It essentially rolls around the Sun. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. A single season on Uranus lasts over 2 decades. It takes 84 Earth years to complete one orbit around the Sun. Neptune takes 165 Earth years. A child born on Earth today will not see Neptune complete even one full orbit in their lifetime. Time behaves differently here. Slow, expansive, measured in generations. The ice giants are composed of water, ammonia, and methane ices. Their blue color comes from methane in their atmospheres absorbing red light. They are not solid, not icy like frozen lakes, but thick atmospheres over deep, exotic interiors. Winds on Neptune can reach speeds of over 2,000 kilometers per hour, faster than any winds on Earth. Storm systems form and dissipate over years. Dark spots appear and vanish. Even at these distances, weather continues. Activity persists. But human presence remains absent. No spacecraft has orbited Uranus. None has orbited Neptune. Only Voyager 2 has passed by. Briefly, quickly, then onward into deeper space. Why have we not returned? Distance, cost, time? A mission to Uranus launched today might not arrive for a decade. A mission to Neptune, perhaps 15 years. Funding cycles, technological updates, political changes, all occur on shorter timescales than outer planet travel. Patience must extend beyond a single career, beyond a single administration. These missions require long-term commitment. If we imagine traveling at 10% of light speed, 30,000 kilometers per second, we could reach Uranus in about 1 day, Neptune in less than 2 days. But such speeds remain hypothetical. Energy requirements are staggering. Shielding becomes critical. Navigation becomes complex. For now, we rely on chemical rockets. Gravity assists, nuclear power for energy, and time. Lots of time. As we drift toward Uranus in imagination, picture Saturn fading behind, the ringed planet now just another distant light. Ahead, Uranus appears pale blue, subtle, quiet. There are no dramatic ring systems visible from afar, no bold stripes. Just a smooth sphere, calm in appearance, but strange in orientation. Then beyond Uranus lies Neptune, deeper blue, darker, colder. At Neptune's distance, the sun's light is faint, but still enough to cast shadows, still enough to illuminate clouds. If you stood on a hypothetical platform above Neptune's atmosphere, the sun would appear small, yet still intensely bright in the black sky. The stars would not fade. Space would feel immense, even more immense than before, because by this point, Earth is not merely invisible. It is lost in the glare of the sun. Our entire inner solar system becomes a tiny cluster near a distant star. Reaching Uranus or Neptune requires acceptance of long silence, long drift, long waiting, data transmission at limited bandwidth, tiny trickles of information crossing billions of kilometers. Voyager 2's signals today are incredibly faint, detected by massive radio antennas on Earth. Each bit of data precious, each message taking hours to arrive. The ice giants represent the threshold of deep solar system travel. Beyond them lies the Kuiper Belt, Pluto. And then, the vast outer boundary where the sun's influence weakens. We have travelled from months to years, from millions to billions of kilometres. The solar system has unfolded gradually, revealing itself not as a compact family of planets, but as a vast gravitational domain. And yet, we are still within the sun's reach, still within its pull, still bound to its gravity. The journey to the ice giants teaches endurance. It stretches our imagination. It reminds us that exploration beyond Mars is not casual. It is a generational endeavor. And still, the sun remains the center. Still, we have not left home. As we drift now beyond Neptune into the region of Pluto, into the scattered icy bodies of the Kuiper Belt, time will stretch further, and distance will begin to feel almost abstract. The ice giants fade behind us, blue spheres dissolving into darkness. Ahead lies the edge of the planetary system, where the sun becomes just another bright star in a sea of others, and where travel time begins to feel almost infinite. Beyond Neptune, beyond the last of the major planets, the solar system does not suddenly end. There is no wall, no boundary line, no final marker. Instead, it thins, it stretches, it becomes more subtle. And scattered across this distant region are icy worlds, fragments of formation, frozen remnants from the earliest days of our solar system. The most famous of them is Pluto, once called the 9th planet, now classified as a dwarf planet, but still a world. Pluto orbits the Sun at an average distance of about 39 astronomical units. That is nearly 40 times farther from the Sun than Earth, but its orbit is highly elliptical. Sometimes it drifts closer than Neptune. Sometimes it stretches much farther outward. At its closest approach to Earth, Pluto can be about 4.2 billion kilometers away. At its farthest, over 7.5 billion kilometers. These numbers begin to feel abstract. Billions of kilometers. Distances that take light hours to cross. Light from the Sun takes about 5.5 hours to reach Pluto. When sunlight touches Pluto's surface, it began its journey before sunrise on Earth. Communication delay between Earth and Pluto can reach nearly 5 hours one way. 10 hours round trip. A command sent in the morning might not return confirmation until night. The only spacecraft to visit Pluto was New Horizons. It launched in 2006. It did not arrive until 2015, 9.5 years later, nearly a decade. A New Horizons was fast. At launch, it was the fastest spacecraft ever sent away from Earth, traveling at about 16 kilometers per second relative to the Sun. It did not stop at Pluto. It performed a flyby, a brief encounter lasting only hours, because slowing down enough to enter orbit would have required enormous fuel that would have dramatically increased mission cost and complexity. So instead, it passed by quickly, gathering images, collecting data, and then continuing outward, even at Voyager speed, 17 kilometers per second. Reaching Pluto at 4.2 billion kilometers would take roughly 2,860 days, nearly 8 years. At airplane speed, more than 530 years. At car speed, over 5,000 years. Civilizations would shift, languages would evolve, and the spacecraft would still be traveling. Pluto itself is small, only about 2/3 the size of Earth's moon. Its surface is composed largely of nitrogen ice, with mountains of water ice, plains of frozen methane. It has a thin atmosphere that expands and contracts as it moves closer to or farther from the sun. When New Horizons arrived, it revealed a surprisingly complex world. Heart-shaped plains, towering icy peaks, subtle haze layers in its atmosphere. Even at the edge of the planetary system, there is beauty, there is activity, there is structure. But Pluto is not alone. It resides within the Kuiper Belt, a vast region extending from about 30 to perhaps 50 astronomical units, filled with icy bodies, some small like comets, some large enough to be dwarf planets. Eris, Haumea, Makemake, countless others. The Kuiper Belt is not crowded. Objects are separated by millions of kilometers, but it is dense compared to the empty regions between major planets. Crossing the Kuiper Belt at Voyager speed would take years. New Horizons, after passing Pluto, continued deeper. In 2019, it flew past a small Kuiper Belt object named Arakoth, more than 6.5 billion kilometers from Earth at the time. Even that brief encounter took years to plan, years to reach, years to communicate. Beyond the Kuiper Belt lies something even more distant, the heliosphere, a vast bubble formed by the solar wind, charged particles streaming outward from the sun. This bubble defines the region where the sun's influence dominates. The heliopause is the boundary where the solar wind slows and meets the interstellar medium. Voyager 1 crossed this boundary in 2012, after 35 years of travel. Voyager 2 followed in 2018. But even crossing the heliopause does not mean reaching another star. It only means entering interstellar space. Still within the sun's gravitational influence, still far from the next stellar system. Beyond the heliosphere lies the Oort cloud, a hypothetical spherical shell of icy bodies, believed to extend from about 2,000 astronomical units to perhaps 100,000 astronomical units. At 100,000 astronomical units, you are nearly halfway to the nearest star. Voyager 1, traveling at 17 kilometers per second, would take roughly 300 years to reach the inner Oort cloud, and perhaps 30,000 years to pass through it entirely. 30,000 years. Longer than recorded human history, longer than agriculture has existed, longer than the pyramids have stood, and still not at another star. This is the true edge of our solar system. Not Pluto, not Neptune, but the farthest reach of the sun's gravity, and even that is only halfway to Proxima Centauri. As we drift outward in imagination, picture the sun shrinking further, now just a bright star among others. Earth invisible, Jupiter forgotten, the planets now mere memory. Space between stars is unimaginably vast. The distance to Proxima Centauri is about 4.24 light-years. That is roughly 268,000 astronomical units. More than double the estimated outer edge of the Oort cloud. At Voyager speed, 17 kilometers per second, reaching Proxima would take over 70,000 years. 70,000. At airplane speed, millions of years. At car speed, hundreds of millions of years. Even at 1% of light speed, 3,000 kilometers per second, it would take more than 400 years, generations aboard a single vessel. The Kuiper Belt and the outer boundary teach us something profound. The solar system is not small. It only appears so in simplified diagrams. In reality, it is a vast gravitational domain, measured in billions of kilometers, measured in decades of travel, measured in human lifetimes, and yet we have crossed it. With machines, with patience, with quiet persistence. New Horizons now drifts beyond Pluto. Voyager 1 and 2 continue outward, carrying golden records, messages from Earth, perhaps to be found, perhaps never. They move slowly, 17 kilometers per second, which feels fast, until measured against interstellar scale. The edge of the solar system does not feel dramatic. It feels gradual. Space does not end. It becomes thinner, quieter, less influenced by the sun, but still part of a larger structure. As we leave the Kuiper Belt behind, as Pluto fades into darkness, we approach a different kind of distance, not planetary, not orbital, but stellar. The distances between stars, measured not in astronomical units, but in light years. And the travel time expands accordingly. Months became years. Years became decades. Decades became millennia. The scale has unfolded gently, from Mercury's 6-year orbital insertion, to Neptune's 12-year flyby, to Pluto's decade-long pursuit, and now to tens of thousands of years between stars. The solar system has revealed itself, not as a compact family, but as a vast ocean around a single star, and we have only just reached its shore. Ahead lies interstellar space, the nearest stars, the Milky Way itself, and travel times that stretch beyond human history. For now, rest at the edge, where sunlight is faint, where distance is measured in billions of kilometers, where the sun is no longer dominant, but merely one star among many, beyond Pluto, beyond the Kuiper Belt, beyond the fading edge of the heliosphere. There is no planet, no orbiting world, no glowing sphere awaiting arrival. There is only space between stars, interstellar space. It sounds dramatic, but in truth, it is quiet, extremely quiet. The sun's solar wind weakens, its magnetic influence thins. Charged particles from other stars drift slowly through the darkness. Temperatures are near absolute zero. Not because there is intense cold, but because there is almost nothing at all. Voyager 1 crossed the heliopause in 2012. After 35 years of travel, it entered what we call interstellar space. But it did not leave the solar system entirely. The sun's gravity still extends outward, far beyond the heliosphere. Voyager 1 is currently more than 24 billion kilometers from Earth. That sounds enormous, and it is. Yet compared to the distance to the nearest star, it is only a fraction. The nearest star system is Proxima Centauri, part of the Alpha Centauri system, approximately 4.24 light-years away. That is about 40 trillion kilometers. 40 trillion. Let that settle. Voyager 1 travels at about 17 kilometers per second. At that speed, it would take more than 70,000 years to reach Proxima Centauri. 70,000 years. If humanity had launched Voyager at the dawn of agriculture, it still would not have arrived. If it had launched when the pyramids were built, it would still be thousands of years away. 70,000 years ago, Neanderthals still walked parts of Earth. That is the scale of interstellar distance. And Voyager is not slowing down. It continues steadily outward. But space is vast beyond intuition. Even light takes 4.24 years to cross the distance to Proxima. When we look at that star, we see it as it was more than 4 years ago. Now imagine traveling not at light speed, but at airplane speed, 900 kilometers per hour. Reaching Proxima would take roughly 50 million years, longer than modern humans have existed. At car speed, nearly 500 million years. The continents themselves would have shifted, mountains risen and eroded. Species evolved and vanished, and the journey would still be incomplete. Interstellar space is not entirely empty. There are a few atoms per cubic centimeter, hydrogen mostly, tiny grains of dust, cosmic rays, but compared to planetary distances, it is almost void. And the distances between stars repeat the same pattern we saw between planets, but amplified. Earth to Mars was tens of millions of kilometers. Earth to Jupiter was hundreds of millions. Earth to Pluto was billions. Earth to Proxima Centauri is trillions. Scale compounds, layer upon layer. If we imagine traveling at 1% of light speed, about 3,000 kilometers per second, we could reach Proxima in roughly 400 years, 4 centuries. That is faster, but still beyond a single human lifetime, perhaps achievable by a generation ship, a vessel where descendants of the original crew complete the journey. But such technology remains hypothetical. Energy requirements are staggering. To accelerate a spacecraft even to 1% of light speed requires enormous energy. Einstein's equation, E equals mc squared, reminds us that mass and energy are deeply connected. As speed increases, energy requirements increase dramatically. To approach light speed, energy requirements become nearly infinite. Light itself travels at that speed, because it has no mass. Anything with mass must obey limits. And so, for now, our journeys between stars remain theoretical. But let us slow down even further. Imagine drifting in interstellar space, no sun dominating the sky. Instead, a field of stars, sharper, more numerous, because you are no longer within the sun's bright glare. The nearest star appears brighter than others, but still small, not a blazing orb, just a brilliant point. Between here and there, nothing to see, no landmarks, no passing asteroids, no gas clouds thick enough to notice, just darkness and faint starlight. The Oort cloud extends perhaps halfway to Proxima. If Voyager were to reach the outer Oort cloud, it would take tens of thousands of years, and still, the nearest star would remain tens of thousands of years beyond that. The solar system feels large, but interstellar space is larger still. We often speak casually of traveling to other star systems, colonizing distant worlds, reaching exoplanets. But measured honestly, well, the timescales are humbling. Even if we built propulsion systems based on nuclear fusion, or solar sails propelled by powerful lasers, travel times would remain decades at best. Perhaps 20 to 40 years at a significant fraction of light speed. That is optimistic. Such missions would require unprecedented engineering, radiation shielding, autonomous systems, sustained acceleration and deceleration, because arriving at another star is not enough. You must slow down to enter orbit, and slowing down requires just as much energy as speeding up. Interstellar travel doubles the challenge. Acceleration outward, then deceleration inward, all while crossing trillions of kilometers. Proxima Centauri itself is a red dwarf star, smaller and cooler than our Sun. Its habitable zone is much closer to the star. Planets orbit tightly. One known planet, Proxima b, lies within that zone. But even if it were Earth-like, reaching it remains a monumental task. Light years are unforgiving units. They are honest. They do not shrink. They do not yield. They simply measure the time light needs to travel. When we imagine the Milky Way, we often picture it as a dense swirl of stars. But the truth is different. Stars are separated by vast distances. If the Sun were the size of a grapefruit, Proxima would be thousands of kilometers away, across oceans, across continents, and between them, nothing. Almost nothing. As we drift outward in thought, leaving the Sun far behind, the solar system becomes a tiny cluster around a distant star, eventually indistinguishable from others. The Milky Way stretches across space, about 100,000 light-years in diameter. Our Sun orbits the center once every 225 million years, a galactic year. Humans have existed for less than 1,000th of one galactic orbit. Interstellar travel confronts us with timescales beyond civilization, beyond recorded history, beyond species memory. And yet, Voyager continues, 17 kilometers per second, carrying a golden record. Music, images, greetings in multiple languages, a quiet message drifting between stars. Perhaps to be found, perhaps not, but it moves, patiently, relentlessly, tiny against the scale of the galaxy, yet persistent. Interstellar space teaches humility. It expands our perception of time beyond lifetimes, beyond generations. It reminds us that planets are not close neighbors. They are islands, separated by oceans of vacuum. Even the nearest island, Proxima Centauri, is separated by a gulf that light takes years to cross. And we, traveling at kilometers per second, require tens of thousands of years. We have reached the boundary between planetary exploration and stellar ambition. Beyond this, the scale transforms again, from light years to tens of thousands of light years, from nearby stars to the structure of the Milky Way itself. For now, remain suspended in interstellar darkness, where the Sun is no longer dominant, where Earth is invisible, where the nearest star is years away at light speed, and where time stretches beyond human imagination. We have crossed the solar system. We have passed Pluto. We have drifted beyond the Sun's protective bubble. Now we float between stars, and ahead, faint but steady, are other suns, each one a distant fire, each one perhaps surrounded by planets of its own. For most of human history, we did not know whether other stars had planets. We suspected, we imagined, but we did not know. That changed in 1992. The first confirmed exoplanets were discovered orbiting a pulsar. And then, in 1995, the first confirmed planet orbiting a Sun-like star was detected. Since then, thousands have been found. More than 5,000 confirmed exoplanets, and likely billions more in the Milky Way. Every star you see in the night sky may host worlds, some large, some small, some rocky, some gaseous, some perhaps with oceans, some perhaps frozen. The nearest known exoplanet lies around Proxima Centauri. Proxima b, about 4.24 light-years away, roughly Earth-sized, orbiting within its star's habitable zone. If we imagine reaching Proxima b, we must first reach Proxima Centauri itself, and we already know the time required. At Voyager speed, 70,000 years. At 1% light speed, 400 years. At 10% light speed, about 42 years. 42 years. That begins to feel almost possible within a human lifetime. But 10% light speed is not trivial. It requires propulsion systems far beyond chemical rockets. Perhaps nuclear fusion. Perhaps antimatter. Perhaps giant laser arrays pushing light sails. The Breakthrough Starshot initiative proposes sending tiny spacecraft, lightweight probes propelled by powerful Earth-based lasers, accelerated to perhaps 20% of light speed. Such probes could reach Proxima in about 20 years. But they would not slow down. They would fly past, gathering data briefly, then continuing into darkness. Even slowing down requires enormous energy. To decelerate from relativistic speeds, you must carry fuel or use magnetic braking against the interstellar medium. Both complex, both unproven at large scale. Now imagine drifting closer to Proxima Centauri. The Sun is now just one star among many. Proxima grows brighter, but still small. A red dwarf. Cooler and dimmer than our Sun, its light more crimson. Proxima b orbits very close to its star, much closer than Earth orbits the Sun, because red dwarfs emit less energy. To remain warm enough for liquid water, a planet must orbit tightly. This proximity brings challenges. Tidal locking. One side permanently facing the star, the other in perpetual darkness. Intense stellar flares, radiation bursts. Even if Proxima b is rocky, even if it has an atmosphere, reaching it is not the only challenge. Habitability is uncertain. Now let us consider another nearby system, Alpha Centauri A and B, twin stars orbiting each other, about 4.37 light-years away, slightly farther than Proxima. Several exoplanet candidates have been proposed there. Imagine traveling at Voyager speed toward Alpha Centauri, 75,000 years. At airplane speed, more than 55 million years. At car speed, hundreds of millions of years. Interstellar travel transforms time into epochs. Beyond Alpha Centauri lies TRAPPIST-1, a red dwarf star about 40 light-years away. It hosts at least 7 Earth-sized planets, some within the habitable zone, 40 light-years. Light takes 40 years to cross that distance. At 1% light speed, 4,000 years. At 10%, 400 years. At Voyager speed, nearly 700,000 years. When we speak of exoplanets in documentaries, it often feels immediate. We see artist impressions, colorful skies, ocean worlds, ringed super-Earths. But measured honestly, the distances remain profound. The Milky Way contains perhaps 100 to 400 billion stars. If even a fraction host planets, there may be hundreds of billions of worlds, and yet each separated by light years. Even the densest regions of the galaxy, near its center, have stars separated by trillions of kilometers. Space is not crowded. It is expansive. Now imagine we could travel at light speed, purely as a thought experiment. Reaching Proxima would take 4.24 years. Reaching TRAPPIST-1 would take 40 years. crossing the Milky Way. 100,000 years. Even light, the fastest thing possible, requires 100 millennia to cross our galaxy. That means when you look at the opposite side of the Milky Way, you see stars as they were before modern humans existed. When you look at Andromeda, our neighboring galaxy 2.5 million light-years away, you see it as it was before Homo sapiens emerged. Time and distance are inseparable in the universe. To look far is to look back. To travel far is to commit to epochs. Exoplanets expand our imagination, but they also demand humility, because reaching them requires propulsion systems we do not yet possess, radiation shielding for decades, life support systems lasting generations, or robotic probes traveling alone. The first true interstellar mission, if it happens, may not be crude. It may be tiny, lightweight, autonomous, a silent messenger crossing light years, arriving decades later, sending back a faint signal. And that signal, traveling at light speed, would take years to return. The conversation between stars would be slow, measured in decades. Interstellar exploration forces us to redefine near. 4 light-years feels close compared to 100,000, but compared to planetary distances, it is immense. The journey from Earth to Neptune takes 12 years at Voyager speed. The journey from Neptune to Proxima takes 70,000. Scale multiplies dramatically, and yet the galaxy itself is only one of billions. The observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, each separated by millions of light-years, even at light speed. Crossing from the Milky Way to Andromeda would take 2.5 million years. At Voyager speed, longer than the age of the universe. Travel time becomes cosmic history. As we drift now among neighboring stars, imagine the silence. No sun dominating, just distant points of light. Some with planets, some without. Some young, some ancient. The Milky Way rotates slowly, completing one rotation every 225 million years. Stars orbit the galactic center in vast arcs. Our Sun has completed about 20 galactic orbits since its formation 4.6 billion years ago. The planets orbit the Sun. The Sun orbits the galaxy. The galaxy drifts among others. Everything moves. Everything travels. But the scale is immense. We began this journey asking, how long would it take to reach each planet? We measured months, then years, then decades, then millennia, then tens of thousands of years. Now we measure light years and centuries and epochs. Exoplanets remind us that the universe is full of destinations, but travel time remains the great limiter. Not imagination, not curiosity, but energy and physics. As we prepare to widen our perspective one final time from neighboring stars to the structure of the Milky Way itself, let the scale settle. Planets became distant. Stars became remote. The galaxy now awaits, and crossing it, even at light speed, requires 100,000 years. For now, rest among the stars, suspended between suns, where distance is measured in light years, and time stretches quietly into the vastness. We began close to home, Earth to Moon, Earth to Mars, Mars to Jupiter, Jupiter to Neptune, Neptune to Pluto, Pluto to the nearest star. Each step outward stretched time. Months became years. Years became decades. Decades became thousands of years. Now we widen the lens even further, beyond individual stars, beyond neighboring systems. We step back far enough to see the structure that holds them all, the Milky Way, our galaxy. A spiral system of stars, gas, dust, and dark matter. A vast rotating disk about 100,000 light-years across, perhaps even larger. It contains between 100 and 400 billion stars, each separated by unimaginable distances, and yet bound together by gravity. From Earth's surface, the Milky Way appears as a faint band of light across the sky, a luminous river. Soft, diffuse. It looks small, but that is only perspective. We are inside it, embedded within one of its spiral arms, about 26,000 light-years from the galactic center. The center itself is dominated by a supermassive black hole, Sagittarius A star, with a mass 4 million times that of our Sun. But even that immense object is tiny compared to the galaxy's full size. Let us imagine traveling across the Milky Way from one edge of the galactic disk to the other, at light speed, the fastest possible speed. It would take approximately 100,000 years. 100,000 years. If you left today, traveling as fast as light, you would arrive on the far side long after every modern civilization had changed beyond recognition. That is light speed. Now imagine traveling at 1% of light speed, 3,000 kilometers per second. The crossing would take 10 million years. 10 million. Longer than humans have existed as a species. Longer than most mammal lineages. At Voyager speed, 17 kilometers per second. The crossing would take roughly 1.8 billion years, nearly half the age of the Sun. The scale becomes almost abstract. Even if we imagine 10% light speed, 30,000 kilometers per second, the journey would still take about 1 million years. A million years to cross our own galaxy. And the Milky Way is not unique. It is one galaxy among billions. Let us slow down. Imagine lifting upward from the galactic plane, rising above the disk, looking down. Spiral arms curve gracefully outward. Stars cluster along bright lanes. Dark dust clouds weave between them. The central bulge glows intensely. Globular clusters orbit like distant satellites. The entire structure rotates slowly, completing one full rotation in about 225 million years. Our Sun is moving. It orbits the galactic center at about 220 kilometers per second. That is fast. Faster than Voyager. Faster than most spacecraft ever built. And yet, at that speed, it takes 225 million years to complete one orbit. A galactic year. Dinosaurs lived and vanished during less than one galactic rotation. Human civilization has existed for less than 1,000th of a galactic orbit. When we imagine crossing the galaxy, we must imagine crossing 100,000 light-years. Each light-year is 9.46 trillion kilometers. Multiply that by 100,000. The numbers grow beyond intuitive grasp. And yet, light itself crosses that distance in 100,000 years, which means when we observe galaxies millions of light-years away, we see them as they were millions of years ago. Time and space are inseparable. Distance is frozen time. Travel is the act of moving through time as much as space. Now imagine launching from Earth, accelerating steadily, reaching 10% of light speed. You would pass the nearest stars in decades. You would pass hundreds of star systems in centuries, thousands in millennia. The density of stars near our Sun is about 1 star per few cubic light years. Not crowded, but not empty. As you move toward the galactic center, star density increases. Distances shrink slightly, yet still measured in trillions of kilometers. Even in the densest regions, stars remain separated by vast emptiness. The galactic center lies 26,000 light-years away. At light speed, 26,000 years. At 10%, 260,000 years. At Voyager speed, over 450 million years. By the time you arrived, the galaxy itself would have rotated multiple times. Star positions would shift, spiral arms would evolve. The Milky Way is not static. It is dynamic, slowly changing. Stars are born in nebulae, live for millions or billions of years, then die, some quietly, some in supernova explosions. The heavy elements in our bodies, carbon, oxygen, iron, were forged in ancient stars, scattered across space, incorporated into new systems, into planets, into life. If you attempted to cross the galaxy at Voyager speed, it would take longer than the time between the formation of Earth and today. Civilizations might arise and fall before your journey ended. And yet, from our perspective, the galaxy appears calm, stable, timeless. It is only because its processes unfold over immense timescales. When we look at the Milky Way band across the night sky, we are looking through the galactic disk, across tens of thousands of light years. The light entering our eyes left those stars thousands of years ago, when ancient civilizations were just forming. We began this journey asking about planets: Mercury, Venus, Mars, then Jupiter, Saturn, Neptune, Pluto, then stars: Proxima Centauri, Alpha Centauri, and TRAPPIST-1. Now, the entire galaxy stretches before us, and even at light speed, it cannot be crossed within a human lifetime. The Milky Way teaches scale beyond personal experience. It dwarfs planetary travel. It dwarfs interstellar travel. It exists on a canvas of cosmic magnitude. And yet, it is only one galaxy. Beyond it lies Andromeda, 2.5 million light-years away. Light takes 2.5 million years to cross that distance. At 10% light speed, 25 million years. The scale expands again. But for tonight, we remain within our galaxy, suspended somewhere in one spiral arm, aware that even the fastest possible travel cannot conquer its full width quickly. The Milky Way humbles us. It stretches our imagination. It reframes our earlier distances. Mars felt far. Neptune felt remote. Proxima felt nearly unreachable. And now they seem small within the galactic frame. Travel time grows with scale. Months, years, millennia, millions of years, hundreds of millions, billions. The universe does not resist exploration. It simply measures it honestly. It demands energy. It demands patience. It demands acceptance of time. Scales beyond personal life. As we drift gently now, high above the galactic plane, looking down at 100 billion stars, remember this: we are already traveling. Earth orbits the Sun. The Sun orbits the galaxy. The galaxy drifts through intergalactic space. We are part of motion far grander than any spacecraft journey. The Milky Way will eventually merge with Andromeda. in about 4 billion years. Stars will rearrange, new patterns will emerge. The universe evolves slowly, quietly, immensely. And we, on our small planet, measure travel time in months and years. But the cosmos measures in epochs. As we prepare for our final reflection, in the next part, we will bring everything inward again, from galaxy-wide scale back to Earth, and understand what these distances truly mean for us. For now, remain suspended in the spiral, where 100,000 light-years stretch from edge to edge, where crossing it even at light speed takes longer than recorded history, where scale becomes serene and time becomes vast. We began close to home, with Earth beneath us, with the moon only days away. We measured months to Mars, years to Jupiter, a decade to Pluto, 70,000 years to the nearest star, 100,000 years to cross the Milky Way. Now we pause, not to calculate further, but to understand what it all means, because the numbers themselves are not the story. The scale is. When we first imagined traveling to another planet, it seemed achievable, within reach. Months felt long, but manageable. A human mission to Mars would take 6 to 9 months. That is not unimaginable. It is within a lifetime, within a commitment. But as we stepped outward, Jupiter demanded years. Saturn demanded nearly a decade. Neptune stretched into 12 years or more. Pluto required patience, measured in nearly 10 years of flight. Then interstellar space changed everything. 70,000 years to Proxima at Voyager speed. Even at 10% of light speed. 40 years. And crossing our galaxy at light speed. 100,000 years. Travel time grows not linearly, but exponentially. Each layer of scale multiplies the previous one. And yet, there is something peaceful about that. The universe is not hostile. It is simply vast. It does not block us. It does not push back. It merely extends. It unfolds outward, measured in light years, measured in millions of years, measured in galactic rotations. The distances we calculated tonight reveal something profound. Human experience is local, deeply local. We evolved for landscapes, for horizons measured in kilometers, for lifetimes measured in decades. Our intuition was never meant to grasp trillions of kilometers, but we have learned to measure them. We have built tools, telescopes, spectrometers, spacecraft. We have sent machines beyond Pluto, beyond the heliosphere, into interstellar space. Even if they travel slowly compared to light, they move. They carry curiosity outward, and that may be the quiet miracle, because the universe does not require us to reach every destination. It simply allows us to try. The travel times we calculated are not failures. They are reminders. Reminders that scale shapes possibility, that energy limits ambition, that patience is part of exploration. When we speak of colonizing distant stars, we must confront physics. Energy scales with mass and velocity. To accelerate faster requires exponentially more fuel. To decelerate requires just as much. Light speed is not merely a number, it is a boundary, a universal constant, and everything with mass must remain below it. That constraint defines the cosmic landscape. It makes galaxies feel large. It makes stars feel distant. It makes interstellar travel a long-term vision. But it also makes something else clear. The universe is old, very old, about 13.8 billion years. Plenty of time has passed for stars to form and die, for planets to coalesce, for life to emerge. If intelligent civilizations exist elsewhere, they face the same constraints, the same light speed limit, the same energy challenges. Perhaps that is why the night sky is quiet, not because life is rare, but because distance is immense, because travel takes time, because communication takes years. When you look at a star tonight, its light began its journey years ago. When you look at the Milky Way, some of that light began thousands of years ago. The farther you look, the further back in time you see. Space is time made visible. Distance is history. And we began by asking, how long would it take to reach each planet? Now the answer feels layered. Mercury may take years of careful maneuvering. Mars may take months. Neptune may take over a decade. Proxima Centauri may take tens of thousands of years. Crossing the galaxy. Longer than civilization has existed. And yet, Earth remains here. Just one astronomical unit from the Sun. Perfectly positioned. Orbiting steadily. The Moon only 3 days away. Mars within months. The outer planets reachable within years. The stars within reach of imagination. Perhaps that is enough, because while physical travel is slow, understanding travels faster. We have already visited thousands of exoplanets. Through light, through data, through telescopes capturing tiny dips in brightness. We have mapped galaxies millions of light years away. Without leaving our orbit, our minds travel where our bodies cannot. Curiosity crosses distances instantly, and knowledge accumulates without requiring decades of propulsion. Travel time through the universe reveals something comforting. The cosmos is not crowded. It is spacious. It is patient. It evolves slowly. Stars live billions of years. Galaxies rotate over hundreds of millions. Even cosmic collisions unfold gradually. We are part of that timeline. A brief moment in galactic history, but not insignificant, because we are aware, we measure, we ask, and that act itself connects us to the vastness. Imagine standing on Earth again, looking up at the night sky, knowing now, the Moon is days away, Mars months, Jupiter years, Neptune more than a decade, Proxima tens of thousands of years, the Milky Way 100,000 years at light speed. Those numbers do not diminish the sky, they deepen it. They make each star more meaningful, because each point of light represents distance, time, history, scale, and yet, despite all of it, you are here, on a planet orbiting a star, within a galaxy, within a universe that stretches beyond imagination, already moving, already traveling. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galaxy at 220 kilometers per second. The galaxy drifts through space, without rockets, without engines. We are carried along, part of cosmic motion far grander than any spacecraft. Perhaps that is the final perspective. Travel is not only about leaving, it is about recognizing that we are already in motion, already part of the journey. We do not need to cross the galaxy to be connected to it. We already are. The atoms in your body were forged in ancient stars. The iron in your blood once lived inside a supernova. The oxygen you breathe was created in stellar cores. In that sense, You have already traveled across the galaxy, across billions of years, long before you were born. Travel time in the universe is vast, but existence itself is cosmic. We are the product of long journeys through space and time. So when we ask how long it takes to reach each planet, we are really asking how scale shapes us, how distance humbles us, how physics guides possibility, and perhaps how patience defines exploration. As this journey closes, let the numbers fade gently. Months, years, thousands of years, millions, light years. Let them soften. What remains is not calculation, but perspective. The universe is vast, but it is not unreachable. It unfolds slowly, and we unfold with it. Tonight we traveled from Earth to the edge of the solar system, to the nearest star, across the Milky Way itself, not physically, but thoughtfully. And that is a journey that requires no fuel, no gravity assist, no launch window, only curiosity and quiet reflection. Now, return gently, back to Earth, back to the small blue planet orbiting one star among billions, back to a sky that feels both larger and calmer than before. The universe continues expanding. The stars continue shining. Voyager continues drifting, and Earth continues turning quietly beneath you. Rest here, in motion, in scale, in perspective. The journey is vast, but so is the wonder. And for now, that is enough. And now, we begin to slow. We have traveled far tonight, from the surface of Earth to the moon just days away, from Mercury's scorching orbit to the frozen edge beyond Pluto, from the nearest neighboring star to the spiral arms of the Milky Way itself. We measured months, we measured years, we measured thousands of years. We stretched our imagination across 100,000 light years of space. And yet, here we are, still on Earth, still beneath a quiet sky, still orbiting a steady star. The journey outward was not fast, it was not dramatic, it was not loud, it was patient, measured, layer by layer, distance expanded. And as distance expanded, so did perspective. When we began, Mars felt far, 6 months felt long. But now, 6 months feels small, because beyond Mars were years, beyond years were decades, beyond decades were millennia, beyond millennia were galactic timescales. The universe did not grow larger tonight. It was always this vast. We simply allowed ourselves to feel it. And there is something calming about that, because the universe is not chaotic in its scale. It is structured, ordered, governed by laws that do not rush. Gravity pulls gently, orbits curve predictably. Stars burn steadily for billions of years. Galaxies rotate without hurry. The cosmos does not race. It unfolds, and we are part of that unfolding. Right now, as you rest, Earth is moving. You are traveling 30 kilometers every second around the Sun. The Sun is moving 220 kilometers every second around the center of the Milky Way. The galaxy itself drifts through intergalactic space, without engines, without fuel, without effort. You are already a traveler, already crossing distances beyond imagination. Without leaving your bed, the planets we discussed tonight, Mercury, Venus, Mars, Jupiter and Saturn, Uranus and Neptune, Pluto and the Kuiper Belt, they continue orbiting, exactly as they did before we began. Voyager continues drifting, 17 kilometers per second, carrying a golden record, a quiet message from a small blue planet. Perhaps it will travel for millions of years. Perhaps it will never be found. But it moves, and that movement matters. Because exploration is not defined by arrival. It is defined by motion, by curiosity, by asking questions that stretch beyond comfort. How long would it take to reach each planet? The answer was never simple. Sometimes months, sometimes years, sometimes thousands of years, sometimes longer than civilization itself. And yet, we asked anyway. We calculated anyway. We imagined anyway. That is something uniquely human. We may not cross the galaxy. We may never stand on a world around another star, but we can understand the distance. We can measure the time. We can appreciate the scale. And in doing so, we participate in the universe. There is a quiet comfort in knowing that the cosmos does not demand urgency. Stars live for billions of years. Planets orbit for eons. Galactic rotations take hundreds of millions of years. There is no countdown, no ticking clock in the sky. Only steady motion, steady expansion, steady evolution. The light from distant stars left long ago, traveling patiently across space, arriving here tonight, meeting your eyes. That light crossed years, centuries, sometimes millennia, just to arrive in this moment. And that is beautiful, because it reminds us that time in the universe is not wasted. It is woven, woven into space, woven into distance, woven into existence itself. The atoms in your body were forged in ancient stars. The iron in your blood was born in a supernova. The oxygen you breathe was created in stellar cores billions of years ago. In a way, you have already traveled across the galaxy, across unimaginable spans of time, before you ever looked up at the sky. So, as we close this journey, let the scale soften. Let the numbers fade gently. Light years, billions of kilometers, hundreds of thousands of years. They do not need to feel overwhelming. They can feel peaceful, because vastness does not threaten you. It surrounds you, it carries you, it includes you. You are not separate from the universe. You are part of it, orbiting, drifting, evolving, and just like the stars. Tonight we asked how long it would take to reach the planets, but perhaps the deeper question was this: what does it mean to live within something so vast? And the answer may simply be this: it means we are small, but aware, brief, but conscious, local, but connected to everything. And that is enough. As you settle now, imagine the Earth turning quietly, clouds drifting over oceans, cities glowing softly in the night. Above them, the moon hanging patiently. Beyond it, Mars still orbiting. Farther out, Jupiter's storms still spinning. Beyond that, Saturn's rings casting thin shadows. Uranus rolling gently on its side. Neptune deep blue in the dark. Pluto frozen at the edge. Voyager moving slowly outward. Proxima Centauri shining faintly. The Milky Way arching across space. All of it continuing. All of it steady. All of it calm. The universe does not rush, and neither must you. You are allowed to rest, allowed to pause, allowed to drift gently into sleep while galaxies continue their slow rotations. Nothing urgent is happening in the stars tonight. They will still be there tomorrow, and the next day, and long after. If this journey helped you feel calm, if the scale of the cosmos felt comforting, you can return anytime. There is always another distance to explore, another perspective to unfold. But for now, let the vastness become quiet. Let the numbers dissolve. Let the motion of Earth carry you, and let sleep arrive gently. The stars are steady. The galaxy is patient. The universe is wide, and you are safe within it. Good night.